Okay, so we are starting section 5.3, and this is about the strength of acids and bases. So we've been talking about strong acids and how they dissociate 100%, and weak acids, how they dissociate less than 100%. Now we're looking at ways that we can quantify how strong or how weak an acid is. And the same with bases, we can quantify them. So first off, a value that you've already seen is Ka. This is the acid dissociation constant. It's the equilibrium expression. This is the constant for every acid. Each weak acid has its own constant, and here's what they indicate. A smaller Ka value means it's a weaker acid. So we can derive a new idea, pKa, and this is pretty important. P in chemistry, erase this. P in chemistry means negative log of. And so pKa means the negative log of Ka, which I have here. And there's also a second one, pKb is negative log of Kb. Both of these are on the AP formula sheet. They are in the equilibrium section. This is where all of the acid-base stuff seems to be thrown. It's at the very bottom of the equilibrium. So approximately the bottom 2/3 of the equilibrium section is actually devoted to acids and bases equilibrium. So the pKa is the negative log of the Ka value. And the larger the pKa is, means the weaker acid. It's a little bit confusing, but if you just think that if one goes up, the other one goes down. So a substance with a larger Ka value dissociates more. That means more hydrogen ions in the solution. That means it's a stronger acid. And the pKa is going to go down. Because remember, with the negative log of something, you're looking at the actual exponent of something. So something with an exponent or scientific notation, something like 10 to the negative first, is actually pretty strong. It has a very large Ka relatively, and its pKa is 1. Whereas if you consider something like acetic acid, where its Ka value is something on the order of times 10 to the minus fifth, times 10 to the minus fifth is really 0.0000 and then your first number. It's very small, but its pKa, the negative log of that exponent, would be 5. And so smaller Ka, larger pKa, weaker acid. Sometimes the best bet is, if you're doubting yourself, just get your calculator out and use this formula really fast, and it'll give you an idea. You can figure this out if you had to. Interesting thing, a strong acid, of which there are 8 of them, 7 or 8, it's kind of debatable. So 8 strong acids, the pKa is going to be less than 0, meaning for a strong acid, it's actually going to have a negative Ka value. And we'll see that come up here today. It's going to be a little strange. So we're going to look at example 1a first. And the question says, write the pKa for each of the following acids. Arrange them from the weakest acid to the strongest acid. And they give us 4 values. 3 of them are Kas, 1 of them is a Kb, and 2 of these substances are notoriously absent. If we want the pKa for everything, we have to know the Ka for everything. So the first thing we're going to have to do is fix some issues here. So going through the list, we do not have a Ka for HCl. But HCl is a strong acid, and so it's doesn't really have a Ka value. Its Ka value is, somewhat infinite. But infinity is not a button on my calculator. I don't know about yours. Probably not. And so usually they would just say that it's something on the order of 10 to the 7th power. 10 to the 7th power is, 10 million. Very large number, especially when you consider that all of these are between 0 and 1. This is between 0 and 1. This is somewhere around 10 million. By comparison, that's pretty infinite. Another one that we don't have is H2O. H2O can act as an acid or a base. But we know some information that's helpful here. We know that Kw is a certain number, 1 times 10 to the negative 14th. That comes from your AP formula sheet. Another helpful relationship from the AP sheet is that Kw is the product of Ka and Kb. And so if you want to know what Ka is, you would do 1 times 10 to the negative 14th divided by the Kb, which is kind of confusing. So let's back it up and see if we can figure this out a little bit better. So here's my value for Kw. If we consider that water is neutral, then Ka equals Kb. And so we're really looking at x squared. And so our Ka is 1 times 10 to the minus 7, which should make some sense. So we've covered all of these. We have one last issue here that we have to cover, and that is for ammonia, we are given a Kb value instead of a Ka value. So when you're looking at this one, what we see is NH3 plus water yields NH4 plus and hydroxide. And this gives you the Kb. If we flip this the other direction, NH4 plus hydroxide yields our NH3 in our water. Here it is acting as an acid. And we're going to use the same relationship that we had right here. Kw equals Ka times Kb. So our Ka value here dividing the equilibrium constant of water with the Kb, which we're given 1.8 times 10 to the minus 5th. This is a 14, not a 4. And we end up with a number that is 5.6 times 10 to the minus 10th. Now we have a Ka. So we've covered this for all of them. Now we're looking for the pKa's for every one of these. All right. So let's just go through this list here. And you already know the formula that I've talked about. pKa is the negative log of Ka. And so I'm just going to go through and I'm going to write the pKa's just right above each of these. So the first one, if we're assuming that the Ka of HCl is something on the order of 10 to the 7th power, if you put that in your calculator, it comes out to be -7 for the pKa. And none of the other ones are likely going to be negative, but remember, on the previous page, we had said that strong acids have a pKa less than 0. And so a strong acid, this is going to be okay. HF, we have a Ka, so the negative log of 7.2 times 10 to the minus 4. And we get 3.1. HNO2, nitrous acid, we have 4 times 10 to the negative 4th power, 3.4. Hypochlorous acid, the Ka is 3.5 times 10 to the negative 8th. The pKa is 7.5. H2O, the pKa of this is 7. And NH4 plus, the pKa, negative log of 5.6 times 10 to the minus 10th, comes out to be 9.3. So now we want to write this in terms of increasing strength. So the weakest acid here would have the largest pKa. So I'm going to write this, increasing strength. So here's NH4 plus. It is the weakest of all of these acids, and its pKa 9.3. So the next one, hypochlorous acid, HOCl, with the value of 7.5. Next up would be our water with a value of 7 for the pKa. Then nitrous acid with 3.4. Then hydrofluoric acid with 3.1. And finally, and this is almost like off the scale here, HCl with a pKa of -7. So the weakest acids have the greatest pKa's, and the strongest acids have smaller pKa's. And remember this one, the strongest acid is a negative value for the pKa. Strong acids do. So the next part, arrange the following from the weakest base to the strongest base. And we're still in example 1, we're still using some of the same numbers, but we're looking at bases now. Chloride, fluoride, nitrite, hypochlorite, water, and ammonia. So the weakest to the strongest base. Now we just did weakest to strongest acid, so this list, weakest to strongest bases, is going to be the reverse of the list that we just had. So let's go ahead and write this in. So hydrochloric acid was the strongest base, and Cl minus is going to be the weakest base. Excuse me. HCl was the strongest acid. Cl minus is going to be the weakest base. And on this one, I'll use a different color. The conjugate base of a strong acid is neutral. This is not going to pull hydrogens out of the water in order to form HCl. They are completely separated once they're in water. And so it's not going to affect the pH. It's not going to pull hydrogens. It's not going to give away hydrogens at this point. Cl minus is neutral. Then the next one, the next weakest acid, which would be, let's see here, fluoride. Excuse me, the next weakest base. We're going to go ahead and arrange these, and then we'll put in some numbers for them. NO2 minus nitrite, OCl minus hypochlorite, H2O, and NH3. So let's just look at the KBs for all of these. So the KBs for all of these. For chloride, the Ka was, infinitely high, which means the Kb is going to be infinitely low, and we're just going to say 0. For fluoride, the Ka value we're given is 7.2 times 10 to the minus 4th, and so what we're going to do is use the Kb and the Kw divided by the Ka for all of these. So 1 times 10 to the negative 14th for water divided by the Ka of these specific acids. For the fluoride, 1.4 times 10 to the minus 11th. For nitrite, 2.5 times 10 to the minus 11th. And just in case you're questioning, this number is larger than this number. They both have the same base. And don't mark this out, but I'm going to do it. If you get rid of this times 10 to the minus 11th, because both of them are the same, you have 1.4, which is smaller than 2.5. That only works when they have the same base with the exponent. All right, hypochlorite comes to be 2.9 times 10 to the minus 7th. Water, 1 times 10 to the minus 7. And NH3, they gave to us at the top of the page, 1.8 times 10 to the minus 5th. Now, you could do a PKB if you wanted to here, but it doesn't ask for PKB, and so we're just going to leave it alone. Some other pieces of information. The conjugate base of a weak acid is a weak base, and that's the premise for all of these ones. Another piece of information. The stronger the weak acid, the weaker the conjugate base. And like I said, eventually you get to the actual strong acids, and they are not acting as a conjugate base at all. They're just a neutral salt. Example 2, determine whether each of the following salts is acidic, basic, or neutral in aqueous solution. So we have 4 of these. There is calcium chloride, calcium fluoride, ammonium chloride, and ammonium chloride. So acidic, basic, or neutral. For calcium chloride, when this dissociates in water, we get calcium ions, which do not affect the pH, and we get chloride ions. Chloride is the conjugate of a strong acid. Therefore, this will not change the pH of the solution. Calcium fluoride is going to dissociate 100%. Calcium, again, is not going to affect the pH. But then we have fluoride, and fluoride is the conjugate base of a weak acid. And so what's going to happen is we have these fluorides, and we have waters, and we're going to end up with HF and some hydroxide. And this means that the solution will be slightly basic. In part C, we have NH4Cl, ammonium chloride. Remember, the chloride is not going to affect the pH of the solution, just like here. But this ammonium, maybe. And so we have these ammonium ions and water. And if you look at the Ka that we found for ammonia, let's see here. Oh, here it is, 9.3. It does act as a weak acid. Its pKa is 9.3, so it acts as a weak acid, which means it's going to give one of these away. And so we're going to get NH3s and some H3O plus. And this right here, this is going to produce a slightly acidic solution. And then the last one, we have ammonium fluoride. And we have two things happening here. We have this reaction happening that's making the solution acidic, and we have this reaction that's making the solution basic. And so we need to know what is the pH of this solution. And so we're going to compare their Kas and Kbs. So we have, let's look at ammonia. Its Ka, which we found, was 5.6 times 10 to the minus 10. And for fluoride, we found its Kb, and it was 1.4 times 10 to the minus 11. And we're going to compare these two numbers. So basically, we're going to pick which one of these is bigger. Which one of these numbers is larger, and it's this one. The Ka for ammonium is larger than the Kb for fluoride, and so that's going to tip this towards being slightly acidic.